Hi everyone. In this screencast, I'm going to be talking about effective nuclear charge. We abbreviate effective nuclear charge with Z effective. Z effective is our abbreviation for effective nuclear charge. So what is Z effective, or effective nuclear charge? This is the positive charge that an electron experiences from the nucleus minus any shielding effects from intervening electrons. So it's just like the number of protons in the nucleus, except we have to account for these shielding effects by subtracting them away, and that gives us the effective nuclear charge. So to calculate effective nuclear charge, we take the number of protons and we subtract the number of shielding electrons from it. So let's calculate effective nuclear charge for an atom. If we look at sodium, here's the Bohr diagram for sodium. Sodium has 11 protons and 11 electrons when it's neutral. So to calculate the effective nuclear charge for sodium, we would do Z effective equals the number of protons, which again, you get that from the periodic table. It's 11 for sodium. And if we look at its shielding electrons, it has 2 in energy level 1 and 8 in energy level 2 for a total of 10. And you could also get that from sodium's electron configuration if you were to write it out. So sodium has an effective nuclear charge of 1. To better understand effective nuclear charge, we should look at how it changes across a period. So let's compare the effective nuclear charge for these three elements, sodium, magnesium, and aluminum. So to do this, I'm going to make a table. So in this table, I'm going to have my three elements, sodium, magnesium, and aluminum. And in this table, I'm going to show their number of protons, their number of shielding electrons, and their their effective nuclear charge. Okay, so we've got the number of protons, the number of shielding electrons, and the effective nuclear charge. For sodium, it has 11 protons. We can again see that it has 10 shielding electrons from its Bohr diagram, so it has an effective nuclear charge of 1, just like we calculated already. Magnesium is 1 to the right of sodium on the periodic table. It has 12 protons, but its 12th electron is still in energy level 3, so we haven't added any shielding electrons. So magnesium also has 10 shielding electrons and an effective nuclear charge of 2. Whereas aluminum, we've gained 1 more proton. So aluminum, we have 13 protons. We still have 10 shielding electrons, and our effective nuclear charge goes up to 3, 13 minus 10. So this is showing us that the number of shielding electrons doesn't change across a period, but the effective nuclear charge does increase as you move from left to right across a period. Right? We're going from 1 to 2 to 3 in our effective nuclear charge. And this tells us that aluminum has a higher effective nuclear charge than magnesium or sodium. Let's do the same thing down a group. For lithium, sodium, and potassium, we'll make the same table. Again, we're going to have the number of protons, the number of shielding electrons, and the effective nuclear charge. Lithium has 3 protons, sodium has 11, and potassium, if you look at the periodic table, has 19. Now, for the shielding electrons, we are again accounting inner electrons in any energy level that isn't the core energy level. For lithium, we have 1, 2 shielding electrons. For sodium, we have 2 in energy level 1, and then 8 in energy level 2 for a total of 10. For potassium, if we were to count them all up, we would actually see that we have 18 shielding electrons. So potassium's outer electron is very heavily shielded. The effective nuclear charge then would be 3 minus 2 is 1, 11 minus 10 is 1, and 19 minus 18 is 1. So down a group, my effective nuclear charge is not changing. How does the effective nuclear charge relate to Coulomb's law? Well, we learned that in Coulomb's law, Q1 is the magnitude of some charge. And in our examples, Q2 is the magnitude of a second charge. Magnitude of some second charge. But for us, this second charge is pretty much always an electron. What changes for us is the magnitude of charge 1. And that's because the magnitude of charge 1 is basically equivalent to the effective nuclear charge. So when you see Q1, you should think effective nuclear charge. And when I talk about the effective nuclear charge increasing across a period, for example, you should think an increase in the magnitude of the charge.